Yeah, graphing method. Okay, yeah, let's have a look here. So the first one, what the deal was on the first one, I didn't want you to graph one up. I gave you that graph paper for it. I just want you to do one of these so that you get an idea what the analytical trigonometrical stuff is that you're doing really is. So what you'll do here is you just start at a given location and you just start drawing in the vectors from there. So this is the first one. I think it's 122 if I remember right. And so you just kind of work your way through and draw the vectors in. So what you would do, and I'm not going to do this to scale, and actually I don't have my pen with me even, so it's getting a little rough, but I would start with F1. You're going to use a scale of, what do we got for the scale? Centimeter. It's 50 newtons per centimeter. So that first one, it's 240 newtons. So if you take the 240, and again, forgive me here because I don't have my pen, so it's a little challenging. So 240 newtons, and then you have a scale of 50 newtons per centimeter. That would be the scale. So if you divide that out, you'll get a length in centimeters, right? And that will come out to be 4.8. And you can do that for all of the three vectors. Okay, so that'll be 4.8 centimeters. So that's going to be a line 4.8 centimeters long, and it's going to be at the 20-degree angle. So what you're going to do then, you're going to end up 5, 10 and 4 or something. And I think it's kind of over here is where you end up. So that first one, F1, is going to be like that. Yeah, 20 degrees and 4.8 centimeters. Okay, and that'll get you over here. So that's F1. And then you just go ahead and do that with all three of them. F2 will take you up this direction here. And again, I'm not to scale here, but that'll be, and that's F2. And then F3 will be down and to the right at 75 degrees. So that'll pull you down kind of over here. And again, I can't draw very straight. So that's F3. And then to find the resultant, then what you're going to do is you're going to start at your starting point, wherever that happened to be. And then you just connect it to the end. So your F3 actually ends up being kind of short, or FR, I'm sorry, that would be FR. There's your resultant. And you should, I think I give you the answer on this. You should get something close to mine. You're not necessarily going to get mine, but it ought to be about 2.5 centimeters long when you're done. So roughly 124, 125 newtons, something like that. Okay. And it's just a little graphical exercise is all. Yes, question?
So on, say, this particular problem, are you okay with the math and everything being done on the graph and like this is one page of our homework, or do we need to turn it into the format of the...
Oh, yeah, if I give you a sheet to do the work on,
it's okay.
Just do the work on the sheet and turn it in, yeah. My intent there is to save you time, not to make it difficult or anything, okay? So this one you do graphically, okay? So we all right with that? Okay.
You want the answer converted to force?
Yes. Okay. Yeah, right. I'd like the force. So it'll be 120 some newtons, and give me the angle too. Now I think I give you an answer to that, but it's not like you're going to get my answer. I mean, you know, you're doing it graphically. You're not going to get a perfect answer to it. I wouldn't expect that. And I don't even think I got the perfect answer. I just did it. You know, it's not like I'm doing it any more accurately than anybody else. Okay. All right. So we good with that? That's the first one. Okay, and that's the picture you should have in your head when we're doing all this stuff with vectors. Now, when we're actually doing it analytically, which is 131 and 132,
We kind of went through that in class. And what you would do with that is you would take each of the two vectors, in this case, the 680, which is up and to the left at 24, and the 720 up and to the right at 50, and you would use trigonometry there and break them into components. And as I mentioned, I would like you to start working on your organization of your work. Think about how you're going to do that. Be conscious about it. Just don't think about it and write it down as you're thinking about it on the page. Start thinking about it. How am I going to organize this? Because that's what engineers do. I mean, that's a big part of the culture of engineering and how people do work. They organize it and they just work through it like a spreadsheet. And it's very easy to follow then. It's systematic. You make less errors, all this stuff that we want to do when we start working and building stuff, okay? All right. So that first one there, I worked that out for you. If you're going to do it what I call visually, so to speak, or I don't know if I've got a 24-degree angle there to the left and up. So left means negative x, up means positive. So that's a negative and a positive component. I used a 24-degree angle, so I've got negative 680 times cosine 24, and I got positive 680 times sine 24. Yes?
Did we find 131 in the packet, or is that like online?
No, they're all in the packet. So 131 will be right there in the packet.
And it skips from 122 to 132.
We kind of figured this out last one.
It's on.
Well, okay, now what's going on here is on the packet, I have two kind of sets of sheets. The first one lists all of the problems. So if you go to page 2, or no, it's on page 1. This problem is on page 1.
Page 1 of the problems or page 1 of the packet?
Static homework.
They're the same thing.
Oh, yeah.
We're good? Okay.
Oh, that one, where it says just use analytical method.
Yes, yeah. Now, I'm putting extra pages in there, but I'm doing it, frankly, as a favor to you. That's what I'm doing. So the homework's on pages 1, 2, 3, 4, 5, 6. I put in extra pages where I write up some of the problems for you, but not all of them.
Okay.
Because I want you to learn the method of doing this. But I want to save you some time because I know everyone gets so busy in this second year of engineering, okay? So the homework problems are on pages 1, 2, 3, 4, 5. They are written up. Some of them are written up. And if they are, it's like 1A, 1B, 2A, 2B, that kind of thing. That's how it's organized, okay? Are we all right with that? We good? Yeah. So some of those are written up, but not all, okay? So I don't think 131 is. All right. So what I've got then is I've got a column for fx and a column for fy, and then I've got the 680, okay, on the left, and then I just do the trigonometry. I know I've got a 24-degree angle to the left there with the horizontal. Now, and if I use that, I have to put in the signs myself, okay? And if I want to the other way to do it is just find the positive angle from the horizontal, which in this case would be 156. And you could just use that without having to put the signs in yourself. Okay, you could do it either way. Again, as I've mentioned this also, I don't really care about your method as long as it makes sense and I can follow it, that's fine. Okay, either way. So if I use cosine 24, I have to put the negative in there for fx. If I use the 156, I don't, because the cosine of 156 is a negative number. Okay, all right. So you can do it either way. Now, I prefer the top method because, one, that's how I think. I go left, that's negative, or actually that's the other direction we go. Left is negative. That's how I think about it. The other thing is, when you start working with people who build this stuff, you got to tone down the analytics side of what you're talking about and get a little bit more common sense, because they're people that build stuff and work with their hands and think very visually, and you have to communicate with them, okay? So I don't think, if I go that way, that works. If I start giving them like 156 degrees, they may not like that so much, okay? So that's one of the reasons why I prefer that, all right? Okay, so, but whatever you like is fine with me. And, there's all different ways of doing this. So we okay with that? And then we're gonna do the same thing on the one below. Just break it into components. And then what you're gonna do, you're gonna add them up, see? You add up all the x's, you add up all the y's, and you get the resultant. Okay. And maybe I'll just put a sum sign there so we get the idea, okay? And then to get the total resultant then, what you would do is, there we go, you're gonna get negative 158.4i and 828.2j. Now, if you round that to the nearest Newton there, that's fine. You might just get negative 158 and positive 828. That would be fine, okay? And then you take the square root of some of the squares and get the magnitude. It's going to be 843 newtons. And then you can do the arctan, the tangent to the -1, which is also, you know, that's how it's probably listed on your calculator. And you're going to do that for sum of fx, sum of fy on the top, and sum of fx on the bottom, okay? And you're going to run that. And that will get you the angle. But remember, the angle will, by default, is in quadrants 1 and 4. And if your answer is not in quadrant 1 or quadrant 4, which this one is not, you have to convert that angle by either adding or subtracting 180 degrees to get the angle that you want. And I might have a typo in your packet. That angle should be 100.8 degrees. So you might be getting a negative, whatever the heck that is, 79.2. Is that what that comes out on your calculator? I'm not sure. I think it does. Or, yeah, 79.2. That sounds about right. Okay. We okay with that? That's the process for finding the 2D resultant there. Okay. We good? Okay, the next one is the same thing. You're doing the same thing, except you're doing it for 3 components, not 2. Okay, so you just break up each of the 3 forces on the next one into x and y components. You got F1, F2, and F3. You break them all up into x's and y's. You add up some of fx and some of fy. You take the square root of some of the squares, and then you take the arctan of sum of fy over sum of fx. So that's the next one. It's the same process, just one more vector. So, are there questions on actually that's 132, isn't it? 132? Yeah, 132. We got any questions on that? All right. Okay. All right, and then there's one more to do after that. It's 141. All right, now 141, there's an approach to that, okay? So let's kind of have a look, and this is what we were doing yesterday. You have 2 forces there. You've got F1 and F2. You want to look at the dimensions on that and get the angles that they make with the x, y, and z axes. So what you're looking for here is how the force is connected to the axis. So F1 has a 72.36 degree angle with the x-axis. With the y-axis, it's coming over here, 120.34. And then with the z, we're going up there, 36.09. Right? So you look for those dimension markers that dimension the angles, and you get from the vector to the axis. Okay? And what you then do is you take the cosine of those angles. And what that gets you is a unit vector. Okay? So that's how you get the unit vector. So cosine, the angle with the x-axis is alpha, the angle with the y-axis is beta, and the angle with the z-axis is gamma. So the unit vector is cosine alpha, cosine beta, cosine gamma. Now the other thing you might notice there is I'm using more of a math notation because I don't like writing in I, J, and K all the time. So I'm putting in those cosines, I have a space between them. That's how they do it often in math classes. So that's often how I do it because it's just more efficient and don't have to write I, J, and K all the time. You all with me there? You know, I is the x unit vector, J is the y unit vector, and K is the z unit vector. You don't have to put that in there. If you could, they do this in this way in math class sometimes. Yeah, right. I don't know what they call it. It's vector notation. So yeah, okay. That's fine. That works well. Okay, so we good with that? So that gets me my unit vector. What that thing does is that points in the direction of F1. That unit vector will be proportioned out into x, y, and z components to point in the direction of F1. Okay? So then if I scale that vector up by 70, that will get me a force vector. If I scale the unit vector up by 70, I get a vector that has a magnitude of 70 now, because the unit vector has a magnitude of 1. If I scale it up by 70, my new vector has a magnitude of 70, which is what I want, because that's the 70-pound force. And it's proportioned properly so that it points in the right direction. If I just scale this vector up, what I get is the proper x, y, and z components on that 70 magnitude vector that pointed in the proper direction. Okay, that's what's going on there, all right? All right, so I'm just taking the unit vector, which is proportioned properly. Sometimes I think of a unit vector as being a direction pointer. It's a sign that says go that way. And you can just scale it up then, and that resulting vector will point in the proper direction. You can scale it up to however much you want. Okay, so F1 is 21.2, negative 35.4, and 56.6. Okay. So any questions on that bit?
And then you want the sum vector, right?
Yes, so you got to do the same thing for F2.
Yeah.
Now, one thing I want to caution you on F2 is there is this issue of a negative angle in 3 space, which is a little trickier than a negative angle in 2 space. So the safest way to go, and I tend to do this, I tend to do the 2D stuff kind of informally. I just look at it and work out the right angle trig. But 3D, I do it in a more kind of systematic, formal way. What I might want for this vector here is the angle with the positive z-axis, which would be what, 123, is that right?
What, 180, 157?
Yeah.
I think so, yeah.
Yeah, 123. That might be the safer way to go. You got to be a little careful with this because you can't call that negative 57. Okay? The cosine of negative 57 is not right. What you want would be the negative cosine of 57 if you're going to go with that, with the negative component there, okay, with that force going downward. The safest way to do it is just plug in 123 and then don't worry about the negatives, okay? That's the safe way to do it. Are we okay with that? Okay. So just watch that, because what's the cosine of negative 57 is a positive number, see? That's how it works out. So if you're going to use the 57-degree angle, you got to put the negative out in front of the cosine. So you have to do that, all right? All right, and then what you're going to do, you're going to get F2. You've got F1, and then you're going to do the same thing. You're going to get F2, and then you just add up the components is what you do. You just add up the columns. And again, I know I'm overdoing this, but all the same, I'm doing it for a reason. Get the stuff in columns. It's easier to add up columns than it is rows. And there's something about how your eye works. It just works better this way. So work it down like that. Get the sums. Take the square root of sums and get the magnitude. Okay. Okay. So we doing all right with that?
And how do you get the angle?
The angle? I don't know if I asked you for it on this.
Alright.
I don't think I did.
You just asked for the
Yeah, I think that's so. As for now, if you want the angle though, to get the angles with the three axes, you find the unit vector.
Yeah,
So
but I
you-
thought I'd have to turn it into a unit vector again.
You would, if, I don't think I asked you for the angles, but if I did, you'd have to divide through the force vector by 64.3. That'll turn it back into a unit vector, and then do inverse cosines to the three components, and that'll get you the angle.
Pretty much.
All right.
Yeah.
So, we okay with that? Okay. Now, one thing I want to mention about this 3D stuff also is that it's very systematic. There is a process to do these things. I'll cover it in class, and then I'll give you homework that might have a couple little things that are different, but they'll be quite similar. So just get your homework out there and or the stuff we do in class, and just track through it step by step. I've even got a page that outlines the processes to do all of the 3D stuff. And I can't remember what page that is, but one year somebody asked me for that, so I came up with a flow chart for doing 3D, because it's very systematic. There's just ways you do it, and I don't know where the flow chart's at. But it's in there somewhere, I don't know.
Is it 3D equilibrium?
No, it says 325 if you ever, 325 is the page that has I call it the 3D flow chart, because somebody asked me once for one, and so I cooked it up, okay. All right. All right. So that's the stuff that's due on Monday. So there's 4 of them, okay? So give yourself a little time to do these, especially these 3D problems. They do take some time, so don't, budget some time and get those and work through those, okay? We're good? Questions? All right. Okay, a couple more 3D things to do then. If we're okay with the homework. So now we went through the basic 3D and we just covered that homework problem. There's a couple kind of things that can come up in 3D that are more complex. So let's have a look. A couple of what you might call special cases or something like that. I'm on page 190 is where I am. Now, one thing we want to get used to here is a dimensioning system that's being used. When you're drawing up a 3D problem on a flat piece of paper, that involves that makes it a little bit more difficult, It's on a piece of paper. So we have to use some conventions. So what you can do if you have points in what we call 3 space that we want to specify, a common way to do it is with these dashed lines. So you have a dashed line that comes down from the x-axis down to point A. I'm on page 190 is where I'm at. So page 190. So the meaning of that dashed line is it's in the z direction because the dashed line is parallel to the z-axis. Okay, those are parallel. So what that means, and one way to define drafting is graphical communication, right? Because you're trying to communicate things. That means that you're going straight down in parallel to the z-axis. So if you're on the x-axis and you go down in the z direction, what plane is that point A in? XZ, yeah. Now, a mathematician, sometimes they name a plane by the axis that's normal to it. I don't much like that, though. I'll call that the XZ plane, okay? That's where it's at, straight below the x-axis. All right, now if I know that thing's in the XZ plane, why don't you all just take a minute and write down what alpha is, what beta is, and what gamma is. Remember, alpha is the angle with the x-axis, beta is with the y, and gamma is with the z. So we want those three angles, alpha, beta, and gamma for that vector A, FA. Okay. So what do we got for alpha there? Yeah, 50. That's the straightforward one. How about beta? Yeah, it's 90. Now the reason is, and I've got this up here. If FA is in the XZ plane, it doesn't matter where it is in the XZ plane. It makes a 90-degree angle with the y-axis, right? I mean, that vector can be anywhere in the XZ plane because the y-axis is normal to the plane. Y'all with me there? Okay, listen. So it has to be 90. I mean, it doesn't matter where it is in the XZ plane because by definition, the y-axis is normal to the XZ plane. So beta is 90. Okay. It's 90 degrees. Now, if that's so what I've determined now is A is in the XZ plane, so what's gamma going to be? Not quite, close. What's that? 140, yeah. Okay, it's 140. Now, the reason is, and we got to be a little careful with this, but there's a right angle between X and Z. That's 90. You can add that to 40 and get the 140, okay? I'm sorry, you can add that to 50 and get the 140. Now, you got to be careful, though, about added angles in 3 space. Why can I just add 90 and 50? What makes me able to do that? Yeah, they're on the same plane. See, if 2 angles are in the same plane, you can add them. If they're not, you cannot just add them arithmetically, okay? But those are both in the XZ plane, so you can add them up, okay? All right? So that's the deal with that. Okay? And once you got the 3 angles, you can do the calculations on that. You can just take the cosine of the 3 angles. I put the I, J, and K in this one this time. And I get 257I plus 0J minus 306K. And notice how this stuff works out. I mean, this vector is not pointing in the y direction. When I looked at it, it makes a 90-degree angle with the y-axis, and sure enough, cosine 90 is 0. It should be a 0J. There's no force in the y direction, okay? So, okay. So are we doing all right with that? Okay. So that's one special case, and what makes that special is FA is in a given orthogonal plane, as they call it, XZ. Okay. Okay, so that's one example. Now we got another one that's a little bit, little trickier here, and this is what's called a. Are we good with that? We got any questions on that? That one we just did.
Yeah.
I got another example here of what I call a double projection. So let's get F4 written out as a Cartesian vector. Now let's have a look at what's going on here, okay? I've got this point B. Now what plane is point B in? Yeah, the XY actually, XY. Because I'm coming off the y-axis in the x direction. All right, so then I've got this vector that kind of, this, I call it a projection. That is in the xy plane. Okay. Now look at how I'm getting down to point B. I'm coming straight down, aren't I? Oh, shucks, let's see. I'll get rid of that. I want to get some colors here. Come back. And do that. There we go. All right, so I'm coming down in the z direction, aren't I? So what that means is the angle between the red projection here, the vector with the arrowhead on the end, and that line, that dashed line that comes down, what's that angle in there? Yeah, it's a 90, isn't it? Okay, because the red vector with the arrow on the end, that's in the xy plane. The projection dashed line that I highlighted in blue, that's in the z direction. So I've got a z line coming off of the xy plane. There's a 90 in there, okay? All right. So I've got point B is in the xy plane. And I've got a right triangle there, see, with F4 being the hypotenuse. Okay. Now, let's see what else we can do with this. Okay, if I've got that 32-degree angle and I've got this right triangle relationship with that hypotenuse, what is that projection of this vector that I'm drawing here? F4, I'm drawing it dark in black here. What's the projection of that? What's the magnitude of that red vector down there in the xy plane? How would you figure that one out? I got a right triangle there. There's different ways, yeah. I could do cosine 32, right? Times the 800. We good? Okay. And then okay. So I can do that. So that's going to be F4 cosine 32. That's going to be 800 times cosine 32. That's how I get that F4 vector down into the xy plane.
Why does it say F4 is in the XY plane? Is it F4?
That's probably a typo if it does. F4 prime. I've got a prime on that.
Okay.
Yeah, I know the copy isn't the best, but yeah, and you know that's the other thing. I got a few typos in here. I always do. So if let me know if there's something that makes sense. Okay, it's F4 prime is what I'm calling it. Okay. All right, and then now I can also get gamma. Gamma is 58. That's the angle with the z-axis, because if it's 30 degrees from that vector straight down into the xy plane, 90 minus 32 gets me 58. Okay, so 32 degrees down from F4 to the xy plane, that's going to leave 90 minus 32. That'll get me 58 for gamma. Okay. All right. So there's a sketch of what's going on. Okay, F4 is kind of off into 3 space somewhere. If I go straight down at that 32-degree angle, I get to f4 prime, so that's f4 cosine 32. I've got the 58 further up, okay? So now to get this thing as a 3D vector, what I'm going to need to do is take this projection that I show in green, and I'm going to have to project that over to this axis. So I'm going to have to do another projection like that. Okay? You all good? I'm going to have to double project it. F4 cosine 32, but then I'm going to have to do another cosine based on the angle the projection makes with the x-axis. Okay, that's what I'm going to have to do. All right. So why don't we do a little mental gymnastics here? Why don't you put, what I have there is an XY axis with the Z coming out of the page towards us down at the bottom. Why don't you draw in F4 prime on that axis? Where is it? That's going to be a little challenging because this is not, you see how X and Y are oriented up here? They're not oriented the same way down here. So kind of look at that and figure out where is F4 prime on the sketch on the bottom. Okay. And let's say this x-axis is red. Well, I've got it red here. Okay. And then I've got the y-axis is green. It's green there. Okay. So I'm kind of changing how the axes are oriented. So where's F4 prime going to go on that sketch?
The negative y direction.
Yeah, we're just kind of figure it out. See, get it on there, okay? See, this is kind of visualization exercises. We've taken the drafting class with Perry and Rick, you know, the 245 or 248, do a little bit of this stuff. If we're going to do civil mechanical engineering, we want to be able to do this stuff in our mind because we build stuff. We build stuff out in space. We got to be able to see it up there. That helps a lot if we can do that, right? Okay. So that's a 20-degree angle. And here's what I'm looking at there. I'm looking at that x-axis. I got 20 degrees to the x-axis, but I'm not on the y-axis side. I'm on the other side, aren't I? So I kind of have to rotate that in my mind and get to something like that. Y'all good with that? That's below the x-axis, even though they're oriented kind of differently, the axes are, but that's how that projection would be oriented, okay? Questions there?
That angle of 20 degrees,
Yeah.
how did you determine that?
It's given. It's given up top. So this is, you need that. That has to be given too, you know. Okay. That has to be given information. Okay. Okay. So if it's making a 20-degree angle with the x-axis, I'm below the x-axis. 90 more will get me up to the y, so that's the 110. The 110 is 20 plus 90. All right. And then, now I got enough information to get my total Cartesian vector for F4. I can put all this stuff together now. Okay. So I'm going to make a vector out of this thing right here, a 3D vector out of that. Oh, there we go. Okay. So there we go. So I'm going to find F4. I'm going to take 800 times cosine 32 to get me down on the xy plane, then cosine 20 to get me on the x-axis, and that's the I component. That's why I'm calling it a double projection, because I got to bring it down to the xy plane, then swing it over to the x-axis. And then 800 times cosine 32 times cosine 110 will get me the j component. And for the k component, all I need is 58, cosine 58, because that's gamma. Okay? So that's how I'm coming up with that. So I do the 32, cosine 32 gets me in the xy plane. I use that to get onto the x-axis and to get onto the y-axis. So cosine 32, cosine 20i, cosine 32, cosine 110j. But then for the z, I just use gamma. It's just 58. I don't use the 32 for that. I'm just going up 58 to get to the z-axis. And that gets me that F4 vector. You got any questions on that bit? All right. All right, so that's kind of the starting point on these 3D vectors, if we're all right with that. So why don't I get you one more of these to do? I think 143, that'd be a good one. Okay. So 143. We'll make that one due Friday of next week, I think.
Do you have the homework assignments online, like what's assigned?
Yeah, it's listed in Moodle. I keep a running total of it, and I also have a link where people can upload it to. So that'd be the 17th, right? So yeah, there's a running list in Moodle under assignments. Okay. Yeah, question?
Are we gonna be trying for this room every week now, or?
This is our room, and we should have it reserved for the rest of the term. So yeah, we should be in this room for the rest of the term. Okay. It works okay. I mean, that screen's kind of a couple miles away, but other than that, I guess it's not what we got.
The building's quiet though.
Yeah, right. No drilling and no leaks either. We got a big leak going on there. Yeah, okay. All right, so we good? All good? Have a good weekend.
It's like
Okay.
running a drill rig.